Okay, so good morning again. So today we'll start our classes on this platform actually on WebEx, Cisco WebEx meeting platform. Uh, so I think that's why students are joining a little bit late. So we should start now. Actually, I am doing on this platform because I can record the lectures. Otherwise, in Google platform, Google Meet video conference platform, we need to pay for recording. So that earlier that option free of cost recording facilities that is not available now. So I request all the students to join first because I need to allow them. So that's why I'm being distracted a little bit. Okay, so let's start our lecture today. So is my PPT is visible? Students, please confirm.
Yes, sir.
Okay. So today we'll talk about one algorithmic paradigm that is called dynamic programming. It is a kind of the divide and conquer approach you have studied in earlier classes. If we want to recall the divide and conquer approach, then we know that in divide and conquer approach, a problem is solved by dividing it into a number of subproblems and solve them recursively using divide and conquer and combine the solutions to get the solution of the original problem. So the approach of divide and conquer is to divide the problem into subproblems and then find the solution for them and combine them. So here also we do a little bit same. We combine the solutions to the subproblems to get the solution to the original problem. Okay, but there is some differences between dynamic programming and divide and conquer that we'll discuss later on. So in this lecture, we'll have a series of lectures to complete the different parts of divide and conquer technique or paradigm. So it consists of introduction, route cutting problem. That is the introduction to understand that how the dynamic programming approach is used to solve some problems, and matrix and multiplication problem, elements of dynamic programming, longest common subsequence, that is also a problem is solved using divide and conquer, and then finally by optimal binary search tree. So these are the contents we'll be talking about. So as I said that it likes divide and conquer method, and it follows the same kind of approach where we divide the problem and actually find the solutions to the subproblems to get the solutions to the solution to the original problem. But here one important concept which is used or explored in dynamic programming, that is called subproblem overlapping. If you see in dynamic program divide and conquer approach, so we divide the problem into subproblems, and each subproblem is identified as distinct subproblems or problems, and then they are solved. Okay, so all the problems are considered as distinct problems. But in dynamic programming, you see one problem may contain or one subproblem may contain a sub-subproblems that may appear in other subproblems. Okay, so that is the idea of subproblem or shared sub-subproblem. Like there are a number of subproblems, and these subproblems may have common sub-subproblems. Okay, so based on that idea, that is called a subproblem overlapping. Okay, but in divide and conquer approach, we don't find this kind of properties, you can say. So dynamic programming, it is called dynamic programming because it is not a kind of coding we do in dynamic programming. What we do, we store the solutions of sub problems in a table, and then when we the same problem appears, okay, as I said that once sub problems may contain same sub problems. So once a sub problem appears and it is solved once, it is stored in a table. Okay, so when next time that problem appears again, it is looked up from the table itself where we have stored before. Okay, so that's why it is called a programming. This is not a kind of programming coding or what you assume. It's kind of tabularization of the results or solutions. So the idea is to remove the or avoiding the repetition of finding the solution or computing the solutions for the same sub problems. Okay. And other thing is that we use this dynamic programming for finding solutions for optimization problems. So optimization problem is that when a problem have number of solutions, so finding the best one or optimal one, that is called optimization problem. Okay, so we'll be having some minimization problem, some maximization problem. Okay, so we use dynamic programming for finding the optimal value. So we apply this for optimization problems. So here, before applying dynamic programming for any problem to solve it, we need to just a minute. So we need to see that these problems can you see my PPT now?
Yes, sir.
Yes, sir.
Actually, I have just minimized it because I need to see that who are waiting in the lobby for joining. So that's why. Okay. So we need to see that some properties a problem is satisfying or not. Like before applying dynamic programming, what we need to do, we need to follow 4 basic steps to construct a solution. So first thing is to characterize the structure of an optimal solution. So as I said that the dynamic programming approach is used for solving optimization problem. So we need to characterize the structure of optimal solution. That means there will be some mathematical expressions or any kind of representation of the problem so that it will be characterized as the structure of an optimal solution problem or optimal solution. And then we define recursively the value of an optimal solution, that how we need to define the solution, optimal solution using recursive formulas, and then compute the value of an optimal solution in bottom-up approach. And finally, we need to construct an optimal solution from the computed information. So what we say that if we don't need the optimal solution for the problem, if we want to find out the optimal value only, then the first 3 steps, okay, are enough for finding optimal solution. Okay, optimal value, actually you can say value of the optimal solution. But if we want to find the optimal solution itself, then we need to perform step 4 actually. So we'll start with rod cutting problem that will help us to understand the different steps, as I said, or the different properties for one problem must have when we can apply the dynamic program to find the solution for it. So rod cutting is such a problem where we can use dynamic programming, and we'll see that how the dynamic programming concept is used for using rod cutting to getting an optimal solution. So rod cutting problem is nothing but a simple problem that we have a rod of length 10 inch or any kind of unit, and we have a table of or you can say information which stores the prices for the length of different length of the rod. Okay, like pi is the price for length I. Okay, where I may be 1 to n. Okay, so Pn denotes that suppose the length of the rod is n, then Pn denotes that we are not dividing or cutting the rod at all. Directly we are selling. So idea is that there is a company who suppose manufactures rods, and then they cut the rods into pieces, and each piece is having some certain price. So after manufacturing one rod, they want to cut it into pieces so that they can get or obtain highest value out of it. So this is the simple idea, and the problem is we need to find out the position from the left end of the rod where you need to cut so that these two parts will give optimal value of the price. Okay, so this kind of problem which will be optimized using dynamic programming, this is an optimization problem, as I said, and we need to find out the position where you need to cut. So that will be the idea actually. So we'll start with a simple example like this, where you see that the upper table is denoting the prices for different length I from 1 to 10. Okay, and pi denotes the price for each particular length. Here in the example of figure, you can see that from figure 1 to 8, it is denoting all possible cuts for a rod of length 4. Okay, so from the table you can check it that figure A is having a rod of length 4 where we are not cutting at all. So the total So we are not cutting the rod at all. So what it is the optimal value is 9. Okay. In figure B, it is showing that we cut the rod into 2 pieces. One is of 1 length and another is the length of 8. Okay. And from the table you can see for 1 it is 1, length 1, the price is 1, and for length 3 it is 8. So it is also kind of total price we will be getting, that is 9. Similarly, for in figure for C, you can see that the length of 4, the rod is cut into 2 pieces of length 2 each. So the total price is 5 plus 5, that is 10. So using all possible combinations, you can find out that the maximum value we are getting when the rod is cut into 2 pieces, where each the first piece is of length 2 and the second piece also is of length 2. So both are is of length 2. So the total price of this rod becomes 10. Okay. So from this one we can say that if we cut the rod, we don't cut the rod, so the optimal value is 9. In other cases, also, so the figure B and D, you can see that the optimal cost is 9 or price is 9, but only C, where we are dividing the rod into 2 pieces of each 2 length each, so it is 10. So in this way, we need to find out the optimal cut of the rod, so we get the optimal solution, okay, or profit. So this is the procedure what you do. If length of the rod is n, then there would be total 2 to the power n minus 1 different ways to cut the rod. Okay, independent options of cutting. And we assume that the distance length I we are denoting or representing from the left end of the rod. So if I value may be 1 to n minus 1. And each length after cutting it, we can write it as a summation of the length of all the pieces. Okay, like here we can 7 can be written as 2 plus 2 plus 3. That means the length of the rod is 7 and it is cut into 3 pieces. First piece is 2, then 2 and 3. Okay, so in this way you can denote it. And the optimal, so if we have a length of n, then we can write that n equals to I plus I1, I2, Ik up to. So a k pieces, we have cut the rod into k pieces and the total length can be written like this. Okay. And from the revenue, you can say the revenue or you can say the profit of the, after cutting the rod into k pieces, the total price may be Rn equals to Pi1, Pi2 up to Pik. Okay. So we need to optimize this Rn value actually. So this example shows that for different value of I, we can find out the optimal revenue. Like if the R1 is denoting that the optimal revenue for length 1. So from the table you can see that R1 is equals to 1. R2 also, like if the length revenue is 2, like length of the rod is 2, so the optimal revenue is 2, because only we have one option that if the length of the rod is 2 only, then we can cut it into 2 pieces, 1 and 1. So 1 and 1 will be getting 2, 1 plus 1, because for the revenue for or the price of length 1 equals to 1. So for 2 pieces of length 1, that will give you 2. But if you don't cut the rod of length 2, so optimal solution will be 5. Okay. So similarly for R3 you can see that if we cut R3, like the length of the rod is 3, then we can cut into 3 pieces 1 1 1. So that will give an optimal solution 3. But if we cut 1 and 2, so it will give 1 plus 5, that is 6. Okay. And if we don't cut the rod at all, then that will give 8. Okay, so there also we are not cutting into pieces. So similarly, we can find out for other revenues like from 1 to 10. All revenues we can find out by using these PI values for different length of the rod pieces. I 1 equals to n, 1 equals to 10. So if we want to represent this mathematically, okay, where the revenue R n can be like this one, maximum of Pn, comma R1 plus Rn minus 1, comma R2 plus Rn2 minus 2, comma Rn minus 1 plus R1. Okay, so what does it mean? Pn denotes that if we don't cut the rod at all, so that may be one value. And then if we want to cut the rod into pieces, so initially we cut the rod into 2 pieces. The first piece may be R1 and the revenue of the first piece may be R1. That means the length of the first piece is 1 and the length of the second piece, that is the Rn minus 1. So we want to find out the optimal revenue for n minus 1. Otherwise, what we can do, first rod may be the piece of the rod may be 2 and the second piece may be n minus 2. So we want to find out all possible options of cutting the rod into 2 pieces initially, and these things R1, R2 within this expression are denoting the optimal revenue for the parts. Okay, so this is a recursive procedure we are applying here, because we don't know which value will give you the optimal solution, which particular cut or position the first cut will give you the optimal solution. We need to find out all possible options. Okay, so the previous slide shows that if the length of the rod is n, then there would be 2 to the power n minus 1 possible ways to cut the rod. So from this one you can assume that how much the complexity of the corresponding algorithm will have. It is exponential or to the power of 2 on the input. So from this thing, what we want to see that if we can use the dynamic programming. So as we see that dynamic programming is having one particular property that is called subproblem overlapping. So similarly, there is another property that is called optimal substructure property. What does it mean? That if we want to find out an optimal solution for a problem, then one particular optimal solution will contain optimal solutions to the subproblems, okay, within it. So if we find that any problem which shows this property that an optimal solution includes optimal solutions to the subproblems, then that property is called optimal substructure property. And if any problem is having this kind of property, or the corresponding solution is having this kind of property, then we can use dynamic programming. So the same expression I have written here, Rn, that is maximum finding this one. Since we don't know the value, exact value of I, that where the actual cut should be initially, so we need to check all these things. Okay, but the only thing you see that if we want to find out the solution for R1, Rn, then we need to find out the optimal solution for R1 or Rn minus 1 or R2 plus Rn minus 2. So Rn itself is an optimal solution and it contains optimal solutions to the subproblems or the smaller problems. So that is called optimal substructure property. So here this optimal substructure property is present in rod cutting problem. So we will try to implement dynamic programming on it to find out an optimal solution. Okay, with less time, as we see that if we use recursive algorithm for this, the time complexity is exponential. So we will see that how it is exponential. So it is a recursive top-down approach. What do we do? That instead of writing this thing, this Rn equals to maximum Pn R1 plus Rn minus 1, what do we do? We can give a simpler version of this equation where we see that when we cut initially the rod into two parts, the first part we will not consider for further finding optimal solution, because this part we are considering that is giving you optimal solution or adding optimal solution to the original problem, and the second part we are considering that will also be divided into optimal solution, the way of finding the optimal solution. So Rn can be written like this: maximum of, as we are finding all possible values of I to find out optimal solution, what we are doing, we are finding all possible values of I between 1 to n, and Pi is the solution price of the length of the left rod, which we are not considering further, and plus Rn minus 1. So again we will apply the recursive part here. So this is the approach, and we can solve this problem using recursive procedure like this one. So this recursive procedure is named as cut rod, where P denotes the table which stores the prices for all different possible length of the rods. N is the length of the actual rod we are considering now. So the line 1 of the algorithm will say that if n equals to 0, then it is optimal solution having 0 value. And then if it is not, then we set one value q, that is minus infinity. It is used to compare with other optimal solutions or the value of the optimal solutions. So we set the value of q to a very small value to compare with the calculated value. Okay, and here for each possible value of I, what do? We need to find out this expression. Okay, here we recursively call the cut rod for smaller value of length n, or you can say n minus I. So from this one you can see that if we represent this using a recursive tree, recursion tree, then how many times you are calling or making a call to cut rod. Okay, so all possible value of I 1 to n, we need to call the cut rod and then it will be a tree where the total number of nodes may be very high. Okay, because we are exploring all possible values of I. Okay, and for each branches we are doing the same. So here it shows that the cut rod actually there the possibility of cutting the rod in 2 to the power n minus 1 order. So it will be exponential automatically. So you can check it on your computer by writing a code and implementing it. See, you will see that if we increase the value of n by 1, okay, so the time required to compute it will be very higher. For each increasing of length 1, this will increase the time complexity very high. Okay. So why this rod cutting is inefficient? Because you see that if we apply this rod cutting algorithm here, then this graph or this tree denotes that how the different nodes are being explored or being created, or you can say it denotes the call made to this rod cutting problem, rod cutting algorithm recursively. See, initially, if we suppose the length of the rod input rod is 4, then for value 1, if you see algorithm value I equals to 1, then this part will give, this part is the fixed because pi is a constant value, it is stored in the table, but we are making a call to n minus 1, that is 3 minus 4 minus 1, that is 3. Okay, so it will call again for 3 value, and again for 3 it will call for 2, and for 2 it will call for 1. Okay, so in this way you can see that we have a very big recursion tree for this particular rod cutting, recursively rod cutting algorithm. And here also in the graph you can see, or in the tree you can see that same sub problem appears. Here you see that we are calling the rod cutting for length n here. If you can see my cursor, then you can see this here. Okay, and here also the rod cutting subroutine or the algorithm is called up for the same length of 2. So the same subproblem appears again and again, and for each appearance of this subproblem we need to calculate or compute the value for it. So that's why we have the branches for all the possible cut. So if we want to analyze the running time of rod cut, then we can say that the total number of recursive call made to this cut rod algorithm, that will be Tn equals to 1 plus summation of j equals to 0 to n minus 1, because there may be all different possible recursive call to this rod cutting problem. Okay, so and this 1 is actually denoting the first call we are making to the cut rod algorithm. Okay, so from this one, if we want to solve it using any method, then we will be able to prove that the time complexity is becoming order of 2 to the power n, that is exponential. Okay, so the rod cutting problem is exponential when we use recursive method. Okay, but why? We need to find out some other way to get the solution in less time than recursive procedure. So one observation we can make, that if we use a naive recursive solution, that the recursive procedure we are using recursive procedure for solving this rod cutting problem without thinking anything, like we are not using our brain actually at all, that the same problem is appearing again and again for different branches of the recursion tree, but we are computing them again repeatedly instead of using those pre-computed solutions. So here this is the observation, that we solve the same sub problem or sub problems again repeatedly. So what do we need to do? If we do like this, that if we find or encounter one sub problem, first and we solve it and store the solution in a table, any kind of table, then when the next time the same subproblem appears, instead of solving or recomputing it again, we can look up into the corresponding table and find out the solution and use the cut paste tool. Okay, so here only thing we need to use extra, that is memory, because in normal recursive procedure we don't need to use any external memory or extra memory to store the pre-computed values. But if we want to use this dynamic approach, or we want to avoid the solution computing the same subproblem again and again, we can store it in a table, and that's why we need some extra memory. So it is called a time memory trade-off. Okay, and it is you can see, we can see that the total time will coming down up to polynomial. When we use a normal recursive procedure for rod cutting problem, the time complexity is exponential. But if we use this dynamic programming approach, the time complexity comes down up to polynomial time solution. But the one thing you need to remember, that the number of distinct subproblems is appearing or we are encountering during solving the problem, that will be polynomial in terms of the input size. Okay, the number of distinct subproblems should be polynomial, and each subproblem should be solved using in polynomial time also. Then that problem will give you polynomial time algorithm for solving that the normal problem in a recursive way, which shows exponential time complexity. Now, the dynamic programming approach, or the approach we are using, that storing the solution of pre-computed subproblem for further use. So it can be done in two different ways. One is called top-down with memoization, and bottom-up, okay, in storing a table. So in top-down memoization, it is a simple kind of thing. When there is a table, okay, when a particular problem appears, we use the same recursive procedure. But we are avoiding recalculating or repeatedly computing the same problems appears during the solution or during the solving the problem. Okay, so we use some table, that is called memoization, or you are remembering the solutions you have pre-computed before. Okay, so when a particular problem appears in the recursive procedure, if it is not solved earlier, first it will look into the table, and if the result is not found in the corresponding table or the cell in the table, then it will solve it and store into the corresponding cell of the table. So when next time the same problem appears, it will see into the table and use it for finding the solutions for some other problems. So this is called top-down memoization. We start from we call the recursive procedure for the value n. So we start from the n value, highest value, then we go down. That's why it is called memoization. Okay. Sorry, top-down memoization. And then in bottom-up method, we go by the size of the different subproblems. You see that if we want to, we see that the optimal substructure problems characteristic says that one optimal solution contains optimal solutions to the subproblems. That means if we want to find the optimal solution for a subproblem, we need to have the optimal solutions to the subproblems. That means the smaller problems. Okay, so here, based on these notations, the size of the problems, what we do, we solve the problems, smaller problems first, and then we find the solutions for the next upper level, using the solutions of the sub problems we have computed. So that's why this is called a bottom-up approach. Starting from the smaller sizes, we go up to the bigger size or the highest size of the problem. Okay, so that's why it is called a bottom-up method. So in top-down memoization problem, the algorithm is like this. So memo is cut rod. It takes two arguments, P, that is the table which stores the prices for the different length, and N is the length of the rod. And we have an array that R that stores the optimal solutions for, or optimal revenue for this particular problem for different length of the rod. And initially we store minus infinity to each of the cell of the table to indicate that the values have not been computed before. Okay, and then it calls a subroutine that is called memoized card rod auxiliary. It takes three arguments: p, that is the table again, and n is the length of the lot, and r is the revenue. We are table where we are storing the revenue. Okay, so what it is doing, that if the length of the rod we are finding the optimal solution, so it will look up into the table R for the value n. If it is greater than 0, that means the value have been computed before, so it will return Rn. Okay, otherwise if it is not computed, so automatically Rn should be minus infinity. So it is not greater than 0. If n equals to 0, that means the input rod does not have any length, so it will give 0 value, q will be 0. If it is not, then we initialize q to minus infinity to compare with other values, solutions, values of the optimal solutions. So for all values of I, we need to again find out this thing pi plus memoized card rod auxiliary for smaller value of n minus I. But here we are using recursive procedure. But the thing is that when it is calling this memoized card rod auxiliary, it is consulting with this table Rn or R first. Okay, so if the value is already there, we have computed before, so we don't need to compute recursively again. We will get the value from it and it will return the corresponding value to the function. Okay, so this is called memoization, and we will compare the time complexity of it later on. But from this one, you can easily see that the time complexity is asymptotically order of n square. Now, in bottom-up approach, you see that in bottom-up approach, we use that actual dynamic programming. Instead of using recursive procedure, what we do, we consult with the table only, okay, and then we find the solution. So we start finding the solutions for the smallest problem first, then one level up, then one level up again, and finally we reach to the root of the tree if it is represented as tree. So what we do again, in bottom-up approach, we have two arguments p and n, where p is the price of different lengths, as I said, and n is the length of the rod. So r is the storage where we are storing the optimal solutions. Then initially r0 equals to 0 because there is no revenue for any rod of length 0, and then for each value of j 1 to n, okay, for each value of length 1 to n, what we are doing, we are trying to find out the optimal cut. Okay, so here we are doing what, we are finding an optimal cut based on the value of I. Okay, so the length of the, you can see this j is denoting the length of the subproblem, length of the rod, okay, for which we are finding the optimal solution. And within this length I equals to 1 to j, we are finding a position I that will give you two subproblems, okay, or position of the cut that will give you optimal solution to the problem of length j. Okay, so it will consult with the table p and consult with the table r, and will get the solution. So here you can see initially r equals to 0. So if it is 0, then it will be 0. If it is 1, then it will find the value of, from this one, the length 1. It is p1 only. It is p1 because it cannot be cut into pieces. So we will get the value of p1 automatically from the table itself. So in this way, we don't use any recursive procedure. We use the tables for storing the results, and finally and further we use, gradually we use these values for finding solutions for some larger value of input. Okay, so in this way we get it. So here also the time complexity, you can see the running time also in bottom of control, it is also having two nested loop, and the worst case time complexity becomes order of n square. So you can see that how the time complexity gets reduced from exponential time to polynomial time, even in order of n square time, when we use this idea of storing the results in table. So this is the idea of dynamic programming. So up to this, what we see, that we can find the optimal solution because this Rn is returning the optimal value of the optimal solution, but it is not returning the particular cut at different stages. Okay, so that is, if we want to find the particular cards at different stages of the procedure, then we need to find some way to store these card positions also. Okay, so we want to construct the optimal solutions also here. Not value of the optimal solution, but optimal the solutions are optimal solutions. So how we are doing? We are extending the idea of reconstruction solution for rod cutting. What we are doing? We are using extending bottom up cut rod, where we are using another auxiliary storage or storage for keeping the position of the cut, keeping the position of the cut, or you can say the value of I, which is giving an optimal solutions to the sub problem. Here you can see we have added one particular table, that is SJ, which is storing that the position of the optimal cut position I for length J. Okay, so only one more storage we are using, or array we are using, S, which is storing the optimal cut for any length J. Okay, so if we want to find the optimal solutions for this one structure of the optimal solution actually, so what we do, we just call this print cut rod solutions for this value, and it will call this one, and finally from this S value we will be getting the solution for the optimal cut. So it will return the different position of the cuts. Okay, so this is called print rod cutting problem. So in this way we can use dynamic programming for finding optimal solution. So this is the overview of dynamic programming. From this lecture, what we have understood little bit, that one problem which is having certain properties like overlapping subproblem and optimal substructure property. These are the main thing, two things which we need to remember, that if a problem can be solved using dynamic programming or not, because there may be some misconception of considering one problem to be solved using dynamic programming, even it is not possible to solve in dynamic programming. So, and sometimes it is possible to solve the problem using dynamic programming, but you may not have that much of depth to understand it. That problem can be solved using dynamic programming. So from this lecture, we have seen that one problem which can be solved using recursive procedure, but if the recursive procedure can be converted into a simple problem, like where we need to store the values for future use, then that will help us to reduce the time complexity of the problem from polynomial exponential time to polynomial time. So from my side, I think today the topic whatever I wanted to discuss, I have done it. So I want to have questions from you, because this is an important topic and important paradigm which you can use in future also for solving different problems. So if till now, if you have any problem, you can talk to me. You can express your questions. Okay. Because we have other problems also. We'll be talking about that, solving using dynamic programming. But for today's class, I want to get some questions from you. Students, please come forward and ask questions.
Sir, am I audible?
Yes.
Sir, can you share the PPT later, sir? Because everyone is now like getting ready to come to the college for physical reporting. So not all of them are present in the class today. since it's an important
Yes.
topic, sir. From next time, can you share the recorded version of the class, sir?
See, actually, I already share the PPTs with your CS. Okay.
Okay,
So
sir.
that is not an issue. But actually, when your classes are being starting,
Sir, from 11th April, offline classes will start, sir.
so offline classes actually, we need to discuss this thing. Like I have two sections and two sections of separate classes. Okay.
Yeah.
So it will be difficult for me to take. Actually, total I have 14 classes. So
Okay.
14 classes, it is very difficult to take. You
Okay.
see physically. So what we can do that. If we can have online classes, even you come here. Otherwise, if taking one class and then again after 1 hour, the same class I will go for another section. Okay,
Okay.
so I think it is difficult.
Mm.
So if from your side, if you have any solution, you please come forward.
Okay, sir.
Okay,
Okay, sir.
because I think you understand what I'm saying, all of you.
Yes, sir. Um, I'll ask in the class
Otherwise,
group, sir. I will ask for everyone's opinion about that, and I'll let you know, sir.
okay, okay, okay. So thank you for today.
Sir, thank you, sir.
So I'll be all the classes like till 11 at least will be the classes will be on WebEx platform. Okay, and I will be sharing the meeting password and all so that you'll not need the like permission for entering into the class this platform. Okay, otherwise I need to allow everybody by clicking allow this kind of thing. Okay, am I clear?
Yes, sir.
Okay, so thank you.
Thank you, sir.